we're on just finishing this problem of a fin array. So we had it being 53 by 57 millimeters. Thermal conductivity of the material is given. We have a T infinity, and which is 25. And then we have the chip temperature right there on that surface is 75. Okay. They wanted a single parameters for a single fin, okay, and parameters for a fin array. For the single fin, we had heat rate, efficiency, and effectiveness. For the fin array, we had total heat rate, overall efficiency, and total heat rate per unit per volume. Okay. So they gave us design A and B. So we have these two different parameters, 3 by 3 for A, 1 by 1 for B, different lengths. So then there's different number of fins then to fit it on that same base by width of the B2 by B1. Convection coefficients are different, okay, and then we looked at it with thermal circuit, okay, to start off with, and we had these two methods. We had either going with parallel, where we would combine them into one resistor, but looking at an exposed base and then fins, or we just look at the overall fin array resistance. And that's the route we went. Okay, so the overall fin array, we would need the overall efficiency and total area. Okay, and then if we have that resistance, we can get the total heat. All right, so total area, we just have used the number of fins, exposed area of the fin, and the base area, exposed base area. And we went through and got those parameters for the area of the fins, the exposed base area, okay, the overall then fin efficiency, okay, which we required then the single fin efficiency, right? And that's what we have here, which is basically from table 3.5, which assumes adiabatic fin, but then has corrected fin length, LC, for convection. All right, so that's what you see here. So in that equation, we need that corrected length and the parameter M. So did we ever write down the corrected length? No, it doesn't look like it. Oh yeah, we did up here. Okay, LC. All right, then the M, the parameter M, that comes from the fin equation, way back up when we derived the fin equation off of that little sliver of along a fin of that conduction-convection that's going on. When we went through and derived it, we have that parameter was here, and that's where that comes from, that kind of that combined conduction-convection. Okay, that's that parameter M. All right, so let's get back down here. All right, so we need that parameter M, which requires perimeter cross-sectional area. Okay, and then now we can look to see what other parameters they solve for. The fin heat, QF. So that means we needed the resistance of a single fin, which is this equation, which we already have all the parameters above. And then they also asked us for effectiveness, which we also have all these other parameters here. Okay, so we're just rearranging it. And then the total heat rate per unit volume of that heat sink. So we just need the volume, base 1, base 2 times length. Okay. All right, so when we do that, we get, for the single fin, QF 1.8, and then we have 0.475. We have the fin efficiency for a single fin, 0.475. 779, or basically 78%, where we have 0.873 or 87.3%. Effectiveness 31.9, 25.3. Total heat 113, 165. Overall 0.804, 0.909. And then the total heat per unit volume 1.25 times 10 to the 6th, and 7.81 times 10 to the 6th. All right, so which design do you recommend going with?
B.
B, why?
The efficiencies are better and the volumetric heat transfer is better.
Yep.
For B.
Okay. Yep. So why though is the heat coming off of one single fin for design A higher, and we're still interested in design B?
There's a larger surface area for a single fin for A, but B just had a better volumetric heat loss in total.
Yeah, so when you look at a single fin and compare them, there's more surface area in A, but if you look at the total kind of fin array, you're going to have actually more surface area overall in B when you count all the, more fins. So that's what ends up helping. The other thing that helps is the convection coefficient was different. Right? The couple things is we see effectiveness, that showing very good value. We have 25 and 32, and that's basically that the fins are, if we look at the fin, we have this fin versus if there was no fin is what the effectiveness is. So it's 32 times, designing is 32 times more effective than if you just had the surface area of where that fin was at the base. Okay, so those are, very good values there. The other thing, you see the overall heat coming off of design B is great. And we talked about the convection coefficient is different, right? So why don't we just make a heat sink with more and more fins? This one's now 1 millimeter by 1 millimeter. Now, why don't we do even more? Do more fins? What might be limiting us in that case? What is our limit on more and more fins?
The space that the computer allows you to have for this heat sink.
Space, the computer. I mean, you could still have 53 by 57. Let's just make it, instead of 1 by 1, 0.5 millimeters by 0.5, or 0.1 millimeters by 0.1 millimeters, each of these fins. So it's still the same base. Why don't we just make even more?
Is it our manufacturing process?
So the manufacturing process is one big one, right? Getting this, having a manufacturing process to have that space in between them, and cost effective, right? Not just being able to do it, but being able to do it at a reasonable cost. And then the other is the convection coefficient, which we'll talk about more in later chapters. But if you go, the spaces between now even smaller between those channels, now you have to have a higher and higher, say, fan to blow air through there because there's going to be the pressure drop because you have that space between. Okay, and you're trying to make sure you're blowing enough air through it that it has a T infinity between the fins that are close to T infinity, even though it's worked its way between the fins. Otherwise, you're changing that convection coefficient as it's going through all the different fins. Okay, so we have those kind of two limitations on going in smaller and smaller fins. Any questions on this problem before we move on? Okay.